Okay, so this is the second video, and we're going to discuss about the presentation. So, is there any more questions?
You go to the experiment slide. Oh, next is another question. Last one. Yeah. So it's 10,000 image. Two classes. How to class the image here?
Sorry.
What does these two classes here?
Okay. Mean? I need to go back to my. Yeah. So I use this. This is image challenge competition, I think. So this is multi-label. So for an image, it has multiple objects. May contain more. As you can see, an image may contain more than one object label. The information is in images and text, because I think like those images are from Flickr. So some people will make some annotations and some tags when they upload their images. So they are naturally two views. So the task is classification to classify like which which objects are for an image it contains. Yeah. So those are the 20 classes. You can see this is the MAP.
So what is the training data? It's the image itself and what descriptions?
Yeah, like some comments. Some people when they upload their to Flickr, they will they will make some comments like what they were doing, or
maybe they
like
put
it's captions.
Yeah,
not descriptions of the image.
Yeah.
Okay.
Okay. Yeah. Can I go back the slides of the? Yeah. So no.
Next one.
Yeah. Still the same page. The same page.
Oh, okay.
Yeah. Okay. So all methods plus SV and. So on this task, this data is from a shared task or not?
Yeah, it is a public task. It is from this is the competition.
From which year the task, the data?
2007.
2007, and so you use this data and show the better performance of the model.
Yeah.
Okay. And what is the evaluation matrix?
MAP.
What does MAP mean here? Is it the accuracy or?
No. It is mean and variance of the AP average position.
Average.
Yeah, it is kind of evaluation.
What is AP?
Average precision.
Average precision. Okay.
Yeah.
So okay. So this is actually is the precision score of the system performance, right? The difference, the processing of precision score also.
No, this is the AP average precision.
Average precision.
Yeah, it is different.
It's different. So they have a recall score or not?
Recall score.
Yeah. So precision score is usually to show how, such as this system predicted 100 and 10 is correct, then precision score is 1 out of 10, right?
Yeah.
And the recall usually means in the answers there are 100 and how many you get it, the model. Such as if the model predicts 5,000 but the 50 is correct, so the recall score will be 50 out of the correct answer 100.
Let's see.
Yeah, I know this. What is
So there are a lot of measurements, like you said, precision and recall and something like that. But if you just use precision, it may retrieve very small portion, and then although the precision is high, but the recall is low. So MAP is very popular and traditional way in to evaluate the performance of classification images.
So MAP including record score.
Record, yeah, is you see, it is calculated in this way.
If may I, maybe I can explain better.
Yeah.
Cool.
Is the precision computed at different levels of record. So it's kind of combined measure. If it is like in the retrieval task, you compute the precision at different level of recall. So recall at 1 and you compute the precision value. Recall at 2, it means after 2 retrieve the value, you compute again the precision. Then you interpolate the value, and that's the average precision for one question or query. And then you make the mean over all the queries, and you have the map, the mean.
So actually, they have record information there.
It's a lack of combined measure. It's
Yeah.
using retrieval because it takes into account the rank. Because as you go on with the recall levels, you have taken into account the rank. So it's not just the precision over 100 answer, you know? But at every answer, you are computing the precision. So it's a ranked measure of precision, and I think it's that reason because you have used
Oh, I think that's better than simple precision recall and F measure.
That's the information retrieval metric.
Yeah, cool. And could you go to the model section, the spare space and the private space there? No, it cannot change. Can you
sorry.
connect it there?
Sorry.
Yeah. So you expect in this model when you design, you expect the private spaces to be orthogonal. In this way to reduce the dimensions, right? The redundancy.
The redundancy, yeah.
For the spare space, or do you expect and you don't care it? Or
Sorry?
For the spared space, so you don't care what it is.
You mean the shared space?
Yeah.
Yeah, the shared space should be orthogonal to all the private spaces. Yeah, and the private spaces also should be orthogonal. But it is like we use the loss function and the characteristic of autoencoders to make it, which means that we cannot guarantee that they are orthogonal. But we try to use the loss function to push it to orthogonal.
So where is your loss function?
So the loss function is the square loss. So for autoencoder, the objective function is the input should be as similar, as close as to output. So that is the objective function. We use the square loss.
That would be the autoencoder loss function.
Yeah.
And what about the orthogonal denoising?
Autoencoders, it is also in autoencoders, so it is the same. So the only difference is the structure, the disconnection.
So you use the exact same loss function as the normal autoencoder.
Yeah, as normal denoising autoencoders.
Denoising autoencoder,
yeah.
exactly.
So the denoising autoencoders, it will, as you see, I can show you the. Let me see this one. So the denoising part is, let me see. Yeah, this is the denoising part. You can use the trivial denoising or the evenly denoising. So the denoising is like it will expand. It will expand it will whitening, like for the evenly for the trivial denoising, it will whitening like one features, and still wants the output to be as close as the original. So like for a feature, so for example, if a feature is whitened and it doesn't matter, so which means we can easily to just abandon those features. So it's like whitening, and for the evenly denoising, it's like you can choose like for every 10 you get rid of them, and in other ways, the example will be enlarged, so it will get robust. It is actually the same idea as original the denoising autoencoders, but we use its characteristic of its objective function and to enable its the orthogonality. Yeah, that's kind of like trick. Any more questions?
Yeah. When you presented the second evaluation, there is the slide with
The second experiments?
Yeah.
Yeah.
In the second bullet point, you see our method plus SVM.
Yeah.
Do you combine both methods, or is that a comparison?
Yeah, because as you see, the autoencoders it is just a representation. So what we'll get is this. Yeah, I should mention that. Yeah, so this model, you will learn is this. So this is the representation, is the compact version of the original data. So it is just a representation. You need further the classifiers or other like regression or for a specific task. So we just use the SVM because it is a classifier. Also, you could use the deep learning, like because in early version of the deep learning, it is the stacked autoencoders. So it is like the similar way. Or the Boltzmann machine is, yeah.
Have you tried just with SVM for the classification task, or also with other techniques?
Other techniques, yeah. Because that wise, because that task is relatively simple. So the performance of SVM and the deep learning, the neural networks classifiers is not that much different.
Okay.
Yeah, and I have to, as you see, I have like to compare those, the SVM 2K and the multiple kernel to make the Any more questions?
Yes, can you go the slide to the earlier on page?
Earlier?
Yeah, earlier. I forgot which page. So, okay. Yeah, maybe. So for the autoencoder, you mentioned it's like one hidden layer.
Yeah, so there's only one hidden layer. This is input and this is output. So
how about what's the difference if you put more hidden layers of the performance?
Sorry?
Do you try if you put more hidden layers?
More hidden layers.
Yeah, what will be the difference?
But autoencoder, it has only one hidden layer.
Only one hidden layer.
Yeah.
This is a structure.
This is like the this is
because such as in the natural language processing, there are some people in the beginning they I forgot which task, but the one paper is he mentioned usually people use 1 and 2 layers to do the task. It already shows a very good result compared with before statistical methods, but they didn't do further. However, that paper they showed 3 and 4 hidden layers can perform better compared with 2 hidden layers, but the more hidden layers doesn't contribute more. So one of the contribution of that work I read is he tried more hidden layer to see the different performance of the system.
Oh yeah, I have to point out that what we are trying to learn here is the representation.
Okay.
So like the hidden layer is the representation. So like instead of like it is different from like traditional deep learning like convolutional neural network. If you insert more layers, you will performs better because it will get you learn more. But here we just want to learn the presentation instead of like more. But if you want like to add like classifiers also using the neural networks, perhaps you need to put more layers somewhere.
Mm-hmm.
Yeah.
Cool. Yeah, sir.
Let's go.
Mm-hmm.
You can continue.
No, you can.
It's getting a bit late. You have more half an hour, right?
Yeah.
So for me, we can continue. I'm okay. If someone else have questions.
No, okay.
There are more slides, right?
Yeah.
You can continue.
Yeah, like any more questions?
The slides is done, right?
Yeah, the slides
cool.
are done.
Ah, okay, okay,
Yeah.
okay. I thought you would have like more.
Yeah.
Half an hour of slides. Okay,
Yeah,
okay.
that's it.
Okay, so maybe I have one last question.
Yeah.
So you said you use the same loss function
Yeah.
as the denoising autoencoders
Yeah.
function. And typically when you have denoising autoencoders, you would add noise in the form of some Gaussian noise, for example, right, in the inputs and try to recover the denoised outputs.
Yeah.
And you said that what is different in your method is the use of this shared versus private space and how you build the connections between the inputs and the shared and private spaces.
Yeah.
And do you have any ideas on how or why do you endorse orthogonality by using the weights in the way you do?
Yeah, those are the explanations. So in order to make the shared space to be orthogonal to those one, because those are disconnections. So here is the input. So if you use the input to multiply the weights, and this is the hidden layer. So as you can see, the private space and private first space and private second space, they will be orthogonal, and which will make the shared space to be and make the private spaces to be independent of each other. This is private spaces. And in order to make the shared space to be independent of the private space, we assume that there is an information which is private, but still go to the shared space. If it goes to there, then it is no longer independent. But if it goes there, the information in shared space will project or feed forward to the first view and the second view. Because it is fully connected, it will surely go forward. And then those information for the first view, they are noise, right? Because they are private information of the second view. So those are the noise to the first view. And then those noise will enlarge the error of the output to the input. So in order to make the loss less, the training itself will try to restrain the information to private information only goes to their corresponding private spaces, and that's the way.
But
enable orthogonal.
So you obviously want the shared space to have something, whatever is shared between different views should go through the shared space.
Yeah, so shared space is the information which they both have. So the consensus principle. So for each view, they may have something the same. Like the people sitting here, although like we come from different continents, but we are all human beings. So we all have the head, one head, two arms or something, and those are the same. So we want the same part to go to this one. And if it goes to this one, we have saved a lot of information. Although we have like different colors of hairs or eyes, and those will go to this one. So if you want to rebuild a model from those one, we just use a human pattern as the different colors.
Do you use any projection? Do you project your input I mean, what is the features? What are your input features?
The input features are
for one experiment, for any experiment.
Yeah. For example, for the let's say
Pascal experiment.
Like for Pascal, it is the images and the some comments alongside the image.
So I suppose you probably feed this image through a CNN, pre-trained CNN, and you extract features for this image.
Yeah, you can also do that. Oh, sorry. Oh, I can't see. Slide. Oh yeah, as you can see here, you can put images and text. So those for the second experiment, you just put in the image and text.
Yeah, but what I mean is, for example, when you get to the point of auto-encoding, just before having the hidden layer of the denoising autoencoder, you need features.
Yeah.
So to get the image features and the text features, for the image, I suppose you probably use a pre-trained convolutional neural network.
Yeah, or maybe the sift or serve.
Exactly, for example. Yeah. Or for the text, you probably use like recurrent neural networks to encode the text and so on. So what exactly do you use for these cases?
Yeah, so those are the tags and those are the features.
Ah, okay, okay. Okay.
Yeah.
I have a question about the private space and private layer. Is that the dimension of that private layer depends only on the view, the number of views that you have, or
sorry?
The private space.
The private space
is just dependent. The dimension of the private space just
it
depends
is
on
flexible. It can be, in this case, it is 1, but you can say 2, 3, or more.
How do you decide how many?
Yeah, exactly. So, so as you can see in my second experiment, you have to tune that. This is also the hyperparameter.
Okay.
So after, as you can see, I have done like 20 different examples just to try which are the best combination.
Okay.
And for mine, those are our best.
Okay.
Yeah.
So it's still part of the parameter.
Yeah. So so in summary, so it is easy because you don't need easy and practical. It is you just prepare your data and feed into it and run the code, and it is relatively easy to understand. But the only drawback is you have to tune a lot of tuning.
Okay, this page is interesting. Elegant. So, sorry, have you finished your question?
Yeah, no,
okay. So, in this experiment, one experiment you use for the image classification, right? Such as according to what topic this image is, such as cat or.
You can also use in other experiments.
So, can it be used by pure text classification?
Yeah. Also. If you have different descriptors, like if you have different languages.
Such as if we have the same language, but we have different labels to label it, to tag it.
Yeah, like different descriptors.
Yeah. So we can also use it for the tagging classification.
Yeah.
Actually, in language processing, there are a lot of such tasks, right?
Sorry?
In language processing, there are a lot of such tasks to classify the labels. Yeah, such as part of speech tagging. It's also a classification, and for
supersense tagging.
I also did some NER before, the name entity recognition. They will ask you First, you recognize the entity, and then usually we classify into a name entity, personal name, and location name, and So this is also a classification method. I think it's very good to apply it to there because this is a very long time task, but some years ago it's very hot. Now they already promoted to somehow a very high accuracy, but there's still some space to promote the performance. I think it's good to apply that. And it's not difficult for you. You just do it, try it there. And one more experiment. That's very good.
Actually, I was curious about this method because I've read a paper lately about some guys that have implemented a recommender system exploiting this multi-view representation, because one problem that you have with the recommender system is called the cold start problem. So you don't have enough label and information about the user on some domain, and so you can predict what are the next item to suggest to the user. But if you have a prediction on another domain of the same user, so it's like you can use this cross-domain.
The transfer learning.
And they have implemented this. I don't know if you ever haven't heard about that. The structured semantic model for representing in a deep neural network this kind of behavioral information, and then an extension that implements this multi-view on that. But I didn't know what was a multi-view.
Okay.
So today you gave me a very good explanation on that.
Thank you.
So now I can understand a bit better.
And one more thing is, I think we can do a further work soon, because recently we attended a shared task about verbal multi-words expression identification. This year is the 13th workshop. It's with EACL, and we did with the Trinity researcher, Alfredo and Erwan. The task is we need to recognize the multi-word expression of verbal, and further they classified the verbal multi-word expression into different kinds. It actually is a classification task. So firstly, we need to recognize it, and then we need to classify it into different labels. I did clearly because they offered 18 languages, no Chinese, no English. But Alfredo did further analysis, such as the Alfredo make it simplify because I cannot understand. So officially they offered different kinds. Then Alfredo classified into V1, V2, V3, at least 3 or 4 different kinds. I think it depends. I'm not sure because kind of the The tag is such as for multi-word expression, there are different kinds, right? Such as kick the bucket to say someone died, right?
I don't know.
Anyway, they have different kind of such multi-word expression, and they classify it into different categories. And then we need to, if we want to label it precisely, we need to tag exactly what kind of it is. And for the teams who attended this task, they can also do it a simplified way, such as they can also only do, oh, this is a multi-word expression, or this is not. They don't classify it precisely. But if we do further work, officially they offer such data, you can classify into different kinds of multi-word expression. So we can do this soon, actually. Because our shared task, we attended 15 language out of 18. And 3 languages, we achieved the first rank.
This is the task that you mentioned.
Yeah, I mentioned in the Adapt Stance meeting. And for 8 languages, we are number 2nd. But if we use this classification method, we can rank the 8 language also number 1. And we can submit somewhere else.
Absolutely.
That is cool.
And any more questions?
No, it's very clear.
Thanks.
Cool.
Thank you.
Okay, thank you. Good talk. Cool.
available the slides?
Yeah, I have sent to him,
Okay,
and
thanks.
he will show it.
Because there are some references that I want to.
Yeah. We will make it available after the talk.
Thanks.
Yeah.
And